Okay, good morning, everybody. Thank you for joining this seminar at ICN2. And it's a really great pleasure to introduce Luigi Colombo, who is coming from the United States, from Dallas. I think Luigi is one probably of the most COVID-free person in the world. So we are very safe with Luigi. So Luigi is currently working at UT Dallas in the Department of Material Science and Engineering, but he had developed a very long career at Texas Instruments that he joined in 1981. And then he developed several technologies, developing liquid phase epitaxy, chemical vapor deposition process, and applying them to production. He has been working on infrared detectors, IK dielectrics, and something that made him very famous is the large-scale growth of graphene on metallic substrate, which has sparked actually a lot of activities to bring these new materials to application. So he had about 185 patents, which is unbelievable. And so we are very lucky to have Luigi here at ICN2 to give this talk about his vision about two-dimensional materials and defects that are so damaging, detrimental, but that can be also useful for some properties. So Luigi, thank you, and it's your time.
Thank you, Stefan, and good morning, everybody, and thank you, Stefan and Pablo and Jose, for inviting me and bringing me back to Spain. It's really a great pleasure to be back here for many reasons. You know, friends, and Spain is a nice place to be as well. So what I'd like to do today is, talk a little bit about defect in compound semiconductors, and then apply some of those thoughts to the materials. The talk is fairly simple and straightforward, and but I wanted to drive a few points home on the importance of point defects and control, and when to control these defects. Is this working? Okay, so here's the brief outline. So basically, I will tell you a little bit about defect control in cubic compound semiconductors, and specifically the chalcogenides, where I worked for many years. And just to give you an idea, it took us a very long time to actually understand, many years to understand the role and how to control very, very carefully point defects in mercury cadmium telluride, which is an infrared detector, and it's probably the most the highest performance infrared detector that we have. Talk about defect types in both 3D materials and 2D materials, and talk about the importance of the degree of non-stoichiometry. So typically, chemists talk about stoichiometry, meaning the composition of materials and so forth during a reaction. But the degree of non-stoichiometry is a slightly different way of looking at things that chemists actually don't talk about that. It's more of a kind of a material science, solid state physics way of looking at materials, because we're very interested in single phase, high purity, low defect density materials. And then talk a little bit about TMD film growth and defect control. So obviously there are many semiconductors, and the most important and famous are diamond and silicon and germanium, and they have a very nice cubic structure, which is usually referred to as the diamond structure. And then there is the more difficult materials. You add just one element and life becomes actually hell, because you have to learn how to control both elements, and it's not that easy. And when you introduce a third element, it's even worse. And the structure is the same. It's still a cubic structure, and except some of the lattice sites are replaced with a different element. It's interesting because many years ago, when I first went to TI, there was a systems guy who was trying to explain what mercury cadmium telluride was to non-material scientists, non-physicists. And he says, well, mercury cadmium telluride is a little bit like silicon. The only difference is you replace silicon with mercury, cadmium, and tellurium. Not so easy, right? And so the important part is how do you control the composition of this, so the degree of non-stoichiometry for especially for the higher vapor pressure elements, since these have lower binding energies. Defect in this has been extremely challenging, and the reason is that you can have vacancies, you can have precipitates, you can have dislocations, and these dislocations are there mostly because of the poor mechanical properties. Some of these 2,6 compounds, mechanical properties are equivalent to silicon at 1,000 degrees C. So you can imagine how difficult it is to manipulate these materials and make devices close to room temperature or at 100 degrees C, where sometimes you have to bring them to deposit the dielectrics and so forth. Control of defects in TMDs is equivalently difficult, but even more so because you have two interfaces and one layer of metal in between, and you can control one side, but the other side is very difficult. You can do intercalation, but how do you do intercalation between what? Between the selenium and the metal at the bottom or the top? So diffusion is a totally different concept in this case, and so things become even more difficult in these materials, and that's why there are so many people trying to figure them out. So I said some of these things. So basically, the cubic systems, you have silicon and germanium. Germanium, of course, took off very early on in the early 50s. Then silicon came along, and so these guys, were easily accepted. Even though silicon is a very high melting point material and it oxidizes very easily, we're able to harness it fairly easy. Whereas the III-Vs and II-VIs, because of composition control and defects, took a lot longer. And in fact, I'm not talking about silicon carbide, but if you look at silicon carbide, which is also a very refractory material, because it's binary, it's extremely difficult actually to grow, and it'll be unlikely that it'll go up to maybe a 12-inch diameter that many people would like it to go to, just to reduce cost. Two-dimensional, what? I have to do a small one. Okay, sorry. So two-dimensional materials kind of fall in kind of the same category. You have the elemental, silicon and germanium, and you can actually even put tin in there. And then you have graphene and HBN that then you have graphene and the elemental, right? But the elemental ones, the other elemental ones, are mostly metastable, and so it's been really difficult to get people to use them, and because they're even phosphorine is unstable in air, even though it can be grown relatively easily in comparison, let's say, silicene. HBN, extremely refractory. It's a beautiful material, but it needs a catalyst, just like graphene, and it's not as easy to grow as graphene because of the binary nature. And TMDs, one of the probably issues, even in comparison to the III-Vs and II-VIs, is actually there's too many of them. And it's nice to have too many of them, but sometimes you have difficulty choosing. And from a development perspective, I think that it would have been nice to have maybe just a couple that meet the requirements so that we could focus the resources to solve the basic preparation issues. And so here we have, the beauty of TMDs, just like actually II-VI compounds, is that they can span the electromagnetic spectrum from semi-metals to high bandgap HBN. But the problem is when you go to and so this is, the endpoints are good. In the middle, yes, you can select different band gaps, but sometimes you have too many of very similar stuff, and it's taking a long time to determine which one is the right one for my application. And the problem is that it takes a lot of effort to develop the growth processes and annealing processes and preparation. And then the other question is, you do epitaxy. Can you do epitaxy? Do you have the right substrate? Even though you have two-dimensional materials that have a fairly loose lattice matching criteria, you still have the issue of wanting the right substrate. So there are many defects, right? Some people at the beginning, thought there's no vacancies in silicon, but in these two-dimensional materials, in compound semiconductors, there's plenty of them. And you have substitutional defects, you have anti-sites, you have interstitials, and then there's more geometrically complex defects that emerge during the annealing process of these materials, and so you have to contend with those. And those can be, let's say, precipitates. I'll talk a little bit about this later, but because of the narrow existence region of these materials, you can have what's called retrograde solubility, which means that if you're at high temperature and you're in a single phase region, as you cool the material down from high temperature, in some cases you actually can have phase transitions, but in some cases you can have retrograde solubility, and you have precipitates forming. You can have, for example, in tellurides, you can have second phase tellurium forming as you cool down from a high temperature, just because you go from a single phase to two-phase region as you cool down. I'll show you that. And then, of course, you have dislocations and twins and grain boundaries, and all these, you have to figure out when you want to control them and how are you going to control them. So it's not just how, but it's really when, and that's why it's important to select the right substrate, the right precursors, the right growth system, and so forth. And then there's this little thing called stoichiometry, which in chemistry refers to the relationship between the quantities of reactants and products before and during and following chemical reactions. Nonstoichiometry, however, refers to kind of the alloy ratio. So you take, let's say, MOS2, and it is the ratio between molybdenum and sulfur, but it's really within the single phase region. It's, there are actually reports, and I'll show you some data later, where people have looked at or have created molysulfide with as much as 20% sulfur vacancies. That's a huge number. I mean, it's just, and I think that the reason you get that, or you can actually have that kind of high concentration of vacancies, is because of the two-dimensional nature of the material. In the case of 2,6 compounds, for example, like mercury cadmium telluride, you can have as much as 10 to the 19th vacancies, while still is a single-phase material at high temperature. But as you go to low temperature, that equilibrium vacancy concentration decreases. The same thing is true, I think, for molysulfide. At high temperature, you can probably have a very high vacancy concentration, and the material is stable under the right vapor, the sulfur vapor pressure. But as you cool it down, if you don't cool it properly, you can actually have second phases. And if you lose sulfur, you can, above a certain temperature, you can actually form MO2S3, according to the phase diagram. So it's really important to understand what this is, so that you can actually use this even to modify the transport properties. In 2,6 compounds and even in 3,5s, you can actually use this to control the tightness from N to P, depending upon what the background concentration of defects of impurities is. Okay, so here I'll describe this a little bit more in detail. So here we have a very simple phase diagram. That's that of cadmium telluride. Okay, melting point of 1092, and you have cadmium one side, tellurium on the other side. You have cadmium telluride in the middle, and you have various phases depending upon whether you are tellurium rich or cadmium rich. Okay, so but if you focus and expand this midline, the 50% line, what you find is that the cadmium telluride actually exists within this broader compositional range. And this is the degree of nonstoichiometry. So on the cadmium side, it's very small. On the tellurium-rich side, it's very broad. So you can have a lot of cadmium vacancies, but not too many tellurium vacancies. But part of the problem is that if you grow, let's say, here at the melting point, and you cool it down, or you grow on the tellurium-rich side, as you cool it down, once you reach a certain temperature, which could, in this case, this is the tellurium solidus or the eutectic point, you reach 500-600 degrees, you cross this phase boundary, and you actually create tellurium vacancies. Okay. Now, the problem is that we don't have this data for the TMDs. So is the same thing true? What is the width of this existent region? It's probably wider, but at what temperature? So we need to know the temperature dependence of this vacancy concentration and the existence region of any one of the TMDs. And this is the difficulty. If you have one material, you can focus and get as much data as possible. But if you have n of them, one of the things that we tried to do during what I call the Nanoelectronics Research Initiative in the US, I tried to tell the theorists and say, okay, decide what 2 or 3 materials we should develop for for heterostructures, for single layer device and so forth, so that we can focus resources to grow and prepare really high quality material, because it's going to take a lot of effort anyway. And so let's do that, because there's a big difference also between sulfides and selenoids, huge difference, and totally different resource and allocation and so forth. The equipment may also be different. And so, and it's for these reasons and the lack of data associated with the absence or the availability of too many materials. Okay, so this is the interesting thing for 2,6 compounds that may or may not be true for TMDs, or at least most TMDs. And that is that if you take a material like mercury cadmium telluride and you grow at high temperature, you have a certain vacancy concentration of actually the type 2, meaning mercury or cadmium. And the reason is that the mercury vapor pressure is really very high. And at the melting point, it's 50 atmospheres. During the anneal in the solid state, up to, let's say, 700 degrees, you're talking about 20 atmospheres. And then, so at 700 degrees C, 20 atmospheres, vacancy concentration is 10 to the 19th, 10 to the 20th. And then you have to figure out how you decrease this vacancy concentration in order for you to have control of the transport properties. And so what you do is something which is actually relatively straightforward. You take a crystal, you expose it to a mercury vapor in a closed system, like in a closed ampule, and you diffuse the mercury in and fix the vacancy. So basically what, okay, wrong one. Okay, so imagine this is mercury cadmium telluride. So you bring the temperature of the crystal at some temperature, okay? And then you have the mercury vapor pressure, and basically what happens is it diffuses in and actually brings the composition close to the 50-50 point. And so the idea is to take 10 to the 18th that I said earlier here, okay, or 10 to the 19th, and bring it down to a level that's less than 10 to the 14th, 10 to the 13th. And actually it can be easily done. It takes time. The diffusivity is fairly low, and it takes time. So in this particular case, the P to N conversion was done at around 270 degrees, where the diffusivity of mercury is fairly high. But of course, these are bulk crystals. They're not one-dimensional, two-dimensional materials. And when you bring the vacancy concentration down to 10 to the 13th or 10 to the 12th per cubic centimeter, you get a carrier concentration that is N-type below this temperature, and above is P-type. And the N-type-ness is determined by the background impurities. If you had a background of, let's say, acceptors is very high, then obviously you would have to go to a different temperature to get the transition, the type conversion for the material. And so this process is very well developed and so forth. So question is, how do we do that for TMDs? Do we need to do that for TMDs? The vapor pressure of sulfur, and I'll show that, maybe I'm jumping a little bit too much. Okay, so let me talk about the other defects are also important, which there are plenty of in TMDs. Okay, those are dislocations, grain boundaries, and so forth. So this is just the effect of dislocations, okay, on the current density of a P-on-N double layer heterojunction device of mercury telluride. Okay, so this is number of dislocation per pixel. We should have done it in density, but this was done per pixel, and you can see that below a certain number you have a fairly low leakage, but above, you have a high increase, a large increase in current density. And the same thing is true for this R naught A, is that the metallurgical defects really increase decrease the performance of the device, whereas for higher I should say defects at a lower level, less important than, let's say, dislocation or striation and pinholes and voids, tellurium precipitates. You have very good performance. So defects as a whole are really, really critical. And if you look at a surface of, let's say, MOS2, we looked at the geological MOS2 some time ago, and there's a lot of voids, there's a lot of second phase, some of them are below, some of them are at the surface, and these all have to be taken care of. Now, the nice thing about CVD is that actually it can be cleaner than the geological samples, just because we can start off with higher purity materials. But these things have to be taken care of. So what is, how do you control defects during growth, during post-annealing and integration of these materials? And then the other thing you have to really define is what's high quality. High quality is an optical quality, electronic quality, and so that's where the purity comes in and defects come in. And so we have to learn how to not only grow high purity films, but also low defect films with respect to grain boundaries, point defects, and one thing that we didn't talk about is really interfacial reactions with the substrate. You grow on SiO2, but do you get any interaction with the substrate? Why doesn't it maybe delaminate sometimes, and sometimes it does? Is it because it's reacting, especially as you go to higher temperatures? So that's why the substrate selection is really important. And the other one is cooling from high temperature, and this really depends on the degree of non-stoichiometry and what the pressure control or that you have during the cooling. And let's say in the case of molysulfide, do you cool under a sulfur vapor? And how is that different from a diethyl sulfur vapor? Or how is that different from a hydrogen sulfide vapor? Are they equivalent? Maybe yes, maybe no. Maybe you guys know, but I don't know yet. Okay, so we have this temperature time curve for the growth process, and many things go on here that will determine whether you will be successful or not. So you have the heating of the substrate under controlled chemical condition. You need to do a surface treatment. Maybe you do the surface treatment before, but then when you do that, you have to be careful because you want to make sure that there's no adsorbates, there's no particles, there's no other things that any unwanted stuff, right? You look at an STM picture and sometimes really beautiful, it's perfect, and sometimes we have the erroneous thought that the surface that you're actually growing on is the surface that you see in an STM, but it's not. We don't know what it is, and so you have to worry about that because it determines the nucleation process, nucleation conditions. Then you start growing the film, right? And depending upon the flux, let's say the calcogen to metal ratio, you can have many grain boundaries. And maybe sometimes you don't even have grain boundaries. You think you have grain boundaries, but you don't, because when they join, if they're not registered properly, as in the case of, let's say, epitaxial growth and 3D growth of 2,6 or 3,5s or even silicon, you don't have registration. And if the surface also is some three-dimensionality to it, these things don't join. That's why sometimes you have these films, they go over the first film, or you have a bad interface, or even not even an interface. You just have a void, a line void, right? So you have to worry about also extended defects. And then there's a little thing called layer control. So in this case, you have to worry about nucleation. You have to worry about adsorption on the layers on the TMD itself. And well, what if you want to grow a heterostructure? In the case of III-Vs, it's because you get really 3D growth by and large, you can stop and then grow another surface. Even though you have a certain roughness, you have a certain interface roughness. In the case of 2D materials, you really don't want that. And so we have to find conditions that where you have principally single layer growth rather than multi-layer. And then upon cooling, you do have to worry about the two-phase dislocations, stress, CT, and so forth. And then of course you can do post-growth annealing and surface determination and so forth. But the other thing I want to talk about is, yesterday with Christian, we talked a little bit about the precursors and how you decrease or how you control, let's say, carbon. And so this morning I was thinking, and I said, well, if you look at the reaction here, you form the CO because you're not going to dissociate that, and then the rest is kind of these CH radicals, right? And how do you eliminate those? Perhaps one can add something here, okay? And is that what happens when you add the additives? You have different substrates, or you add sodium chloride or what have you. But how about something more simple? How about adding oxygen? Well, you have oxygen in your reactor because you have you don't have a UHV system, right? So you have oxygen. But so how about controlling that? How about intentionally putting it in and then you take it out, right? So you reach a level where you have too much and then you back off to see if actually it has an effect on the elimination or decrease of the carbon. So maybe that's one way of tuning the growth process to the point where you can actually use the diethyl sulfur rather than the H2S or sulfur itself. I'm really concerned about this using amorphous substrates. From a cost perspective, I understand. From a practical perspective, I understand. But if you're really interested in high crystalline quality films, I think it would be better to use a crystalline substrate. And then you have to worry about intentional seeding. Is it you really would like to have a heterogeneous nucleation, just like silicon. Silicon, you have one seed in a 100 kilogram melt. They pull or 150 kilogram melt that you pull at a 100 kilogram solid single crystal of silicon, and the seed is a few millimeters. It might be max is 10 millimeters. So why not try to do the same thing here? But of course, here we have to learn how to functionalize the surface such that you don't get additional nucleation. And I think there are ways of doing that. And then the other thing is, the cooling under the various environments, which I suggested.
Can I ask?
Yeah.
You're concerned about the amorphous substrate with roughness, or is there anything?
No, it's just registration and nucleation. Because you don't have registration, you don't have any. I mean, even though these are two-dimensional materials that don't have a good registration with a crystalline material, you still have somewhat of ordering when you are doing this on a crystalline substrate. Oops. Oh man. Okay, I have to use this guy. Okay, so if you look at the phase diagram of molysulfide. So then there's the temperature. How do you choose the temperature? And the temperature and also the existing region. So this is a very wide existing region. You have 2-3%. Of course, the reports are up to 8, 10, 20%, which I'm a little surprised. So I need to check that. I need to figure out why they say that you can tolerate such a large non-stoichiometry in the film. But what bothers me here for this phase diagram, even though you're growing in a sulfur-rich environment, okay, There could be times when you are under sulfur deficient conditions. And if you are, then you form this MO2S3 phase. I would personally, I would prefer it to be lower. If you cannot ensure that you're on the sulfur-rich side, you have to be careful in not doing this. But so you must actually have enough sulfur vapor pressure to prevent that second phase from forming. So this is the data that I was mentioning in the case of the solenoid, the molysolenoid. You can have you can control basically the IV or the tightness depending upon vacancy concentration or of the selenium. For high, it's then for P for low is P. So and here they say that they have up to 20%. 20% is a lot of material. I actually don't believe it, but I'll have to check a little bit more carefully. And then they have the Raman that they say it's. I think I have to figure out how they measured the vacancy concentration. I think what they did is they looked at the STM pictures and they measured the vacancy on the surface, but they don't know what it is underneath. And then you have to figure out what the uniformity is. Okay, so it's always bothered me, what the vapor pressure of sulfur was over the solid. So yesterday, actually, I looked up some of this data, and finally I found this data on the vapor pressure of sulfur over moly sulfide. This is actually really important. So it's 1 atmosphere at the melting point, which is good. Okay, which means that as you go down to the growth temperature, let's say if you were to grow at 850, it's less than 1/10 of an atmosphere, but it's still very high. And so it's really, really important to keep this in mind. I know that, in order to grow the films, you have to have a high C to M ratio, but even in post-growth processes, during cooling and all that, this vapor pressure is not insignificant and needs to be paid attention to. So tungsten sulfide, slightly different phase diagram, but similar issues, right? You have as you go to higher temperatures, you might have this phase transition, and maybe this is because of the degree of non-stoichiometry that people have reported, and so you have to, this is where a lot of data is required and careful data. To determine what the actual compositions are of these films. So this is some work that we did a few years ago, where we looked, where we compared the simulation of MOS2 and mostly MOS2 growth from compact to fractal to dendritic, depending upon the chalcogen to metal ratio or the flux. And this is the experimental data for MOS2 from Penn State and tantalum sulfide. So obviously you can model it, and you can even find a region within. You can create a phase diagram of flux versus or the CM ratio versus flux that gives you the right two-dimensional crystallized structure that you want, rather than having these fractal dendritic structure. Because when you have a dendritic structure, you can have very high growth rates, and you can have but you also tend to incorporate and have many defects associated with these fractal shapes. And obviously you would like to have growth where you can, as I said before, you have a single seed and you just intentionally grow on the edges of these seeds. And personally, I think that certainly graphene grows like that, and HBN grows like that. And so the question is, how do you minimize the growth of 3D structures in TMDs? And that's where surface nucleation, intentional perhaps, and surface modification really are important. The other thing you have to worry about is doping. This is data from geological MOS2, and we find all sorts of different things like aluminum, iron, silver, cadmium. I mean, the whole periodic table is there, right? With concentration more than 10 parts per billion by weight. So, you know, it's a significant number of impurities. So if you were to put it in terms of per square centimeter, you're looking at here as, for example, gallium is 9 times 10 to the 10th. Germanium is high, and then you have vanadium and titanium, and these obviously can be dopants. Vanadium is a dopant, as you know, this group found out, and so that's a good thing. In this case, the defect density to explain the work function difference is actually up to 8%. It's huge. It's a huge amount. So when I think about what I was doing, you know, 20 years ago on 2,6 compounds, I was thinking about 10 to the 12th, 10 to the 14th, and 10 to the 18th per cubic centimeter. And then you see 8% of the surface can have voids. That's just, you know, it's a little bit outside of the norm, and really need to learn how to control that, because there's so many other variables. There's so many variables that actually don't control, and this is why the performance in one day is one and another day is another one. And so we need to really do as a community a better job of understanding the growth process to the nth degree and defect chemistry. So if I had to grow the material, this kind of a summary, I would, you know, probably select a crystalline substrate. You have to learn about surface conditioning and cleaning, and this cannot be underestimated. It would be nice if you had cluster tools, especially in a university environment, because in a industry, in a clean room environment, you can actually leave things out in a clean room and not have too many problems. You still have to worry about surface stability and so forth, but at least you don't have particles, you don't have all these other issues. So I think it's really important to do this, not only chemically, but even from a practical perspective. You know, the precursor selection, obviously there's the issue of cost and safety. I didn't put safety in there, but you know, that's probably number one, right? And then temperature, impurities, and growth rate. You know, how do you do doping? I think is an interesting thing that maybe needs to be considered. And you really have to do it during the growth process. You cannot go in and introduce dopants afterwards. Why? Because you can do it on the surface. You form a kind of a Janus kind of TMD, right? Where you have maybe N on one side and MP on the other side, but it really doesn't quite work that way, right? So nucleation is really, really critical. You know, we discussed that a lot yesterday. Maybe we need to do intentional patterning and nucleation. And then, you know, the general growth conditions. Should use a thermal process. Rather a plasma process to, especially in the case of carbon, right? Could you kind of mitigate some of the issues by having a plasma process and maybe even go to a lower temperature? Those are things that one can consider doing. Doping and alloying. Alloying, I think, is fairly straightforward with metals. With sulfur, you know, with chalcogen, I think it's slightly more difficult because of the difference in vapor pressure. But what you could do, I think, with the chalcogen, you can even create a Janus structure, or you can create even an alloy on the surface. The first layer is going to be difficult. So there's this asymmetry of the structure that you create when you do things like that. Yeah, post-growth treatments, we talked a little bit, and then the transfer. I think the transfer is probably just maybe as important as all the others, or maybe as difficult as all the other ones above, and needs to be really, really done well. And if you can afford not to do it, it's even better. So that's what I kind of summarized from the things that I've been thinking about and through discussions and overall. And now this is the list of things that Elin, I think, if I remember, from Penn State. And so this is about MOCVD process for epitaxial tungsten solenoid, right? And they say there are 3 critical steps for achieving high quality epitaxial TMDs. Use crystalline substrate. You need a nucleation step, and you need to do a post-growth annealing, in this case under hydrogen solenoid, to get high quality material. And the third point, reduce vacancies, surface nanoparticles. And by following these steps, we're able to realize large area tungsten solenoid. So I think that the path is difficult, but maybe straightforward if we learn from not only the compound semiconductors or cubic systems, but also what other people are doing and what you would do a priori. And would you use, let's say, a priori necessarily carbon-containing precursor? Probably not, right? If you want to achieve really, really high quality stuff, or you have to find a way of reacting, or you need to find a reactant within your chamber there with your that will dissociate and prevent the incorporation of, let's say, carbon in the film. So I think that's I think that's a critical part of the whole TMD process, and I think that that's it.
Thank you
Thank
very
you.
much.
Great, very nice. So we can take questions from the room, and also Alex will tell us if we have questions. Okay. So actually, I actually have one, of course, to start with. It looks like there are many parameters, okay, that could be controlled in order to optimize the growth, because the objective will be to grow the cleanest and the single crystal of TMDs. And but I'm wondering, all those parameters are also dependent on the equipment that you have, on the wafer scale that you aim for, and so these are external parameters to the growth, but they play a role. That's because if you want to have an homogeneous temperature, 300 millimeters is not the same like you know. Right. So what is the process, even if it's empirical, to, for instance, start with an equipment that you can find in at ICN2 and say, okay, let's try to optimize to make the best of it, because maybe we will not be able to make the super nice, super single crystal MOS2, but within this equipment, maybe we can reach the maximum quality that we have. So what is your take on that?
Well, there are some geometries that are better than others, right? One of the first considerations that must be done, I think, with these materials is that chalcogenide tend to be very corrosive. And so you would like to build a system that's non-corrosive. Why? Because in a real fab, you have to worry about particles. And so if you have a corroded surface, these things somehow will make it to the wafer, okay? And so that's not what you want, because, and you don't want it even in a non-industrial environment, because that will create dopants, non-reproducibility of the process, and so forth. So the first thing is, what are you going to make the reactor of? You know, what's the material? Then there's the geometry. Usually horizontal geometries these days are not, the preferred because of uniformity. Okay, you want to have laminar flow, for example, especially if you are at the higher pressure, which is in this case much higher pressure than you would have in a low pressure CVD system. In a very low pressure CVD system, you can tolerate, let's say, a non-laminar flow, because you don't have to worry about fluid dynamics, right, or gas dynamics. So that's one. The other is gas delivery, and the type of gases and so forth, right? And because that has to do with control. So how do you deliver really accurate gases to the surface, and then you can control very carefully. So that's another aspect. And all those things, I think we can, you can sit down and figure out, and even within a given budget, right? You don't have to spend $10 million for these tools to do that. And by the way, a typical CVD system in a clean room in silicon costs just one chamber is $2 million, and that's a single chamber system. If you get a one that's let's say clustered with other, you're looking at 5, 6, 7 million at 300 millimeter. So so the idea is that for $300,000-400,000 or $500,000, you can create a really nice system for a university environment where you can get really high quality material.
Thank you, Luigi. Thanks first for the presentation. I have a general question. You started from the 3D type materials, no cubic materials, and then you moved slowly to 2Ds. And you have talking about tolerance of 2D materials, for instance, to vacancies, to defects, to doping. And then at the end, you were also mentioning, what type of processes we need to develop in order to improve the 2D materials. Many of these processes are involving doping, thermal annealing. So there are steps that are very well understood in bulk materials, how they work, but they are not so well understood yet in 2D materials. So we cannot do like a implantation in 2D materials, right? Like it's done in 3D materials. Sure. So how much do you think that we still need to develop the general knowledge of how to handle 2D materials in terms of standard processes which are using nowadays in clean rooms, and there is not so clear translation to a 2D system, right? Because diffusion is different, you're saying, no? Because 2D materials are differently built and they are more tolerant or less tolerant to certain processes. So until we don't achieve that translation, right, it's going to be very difficult to reach the same level of impurity levels. Right, we are talking about 10 to the 10th, and we have percentage, no?
Well, I think that, purity is probably something that is, okay, so all excellent points. And the purity, I think, is something that it can be done. I don't think that's a showstopper, as we say in the industry. The part that's probably the most obvious and most difficult is surface conditioning. And if you can do that, then it's the growth rate, okay? And that is if you want to grow large single crystals of the stuff. And it depends on the application, okay? But let's think about something else, right? What if you can actually grow a single crystal and you only need 10 or 20 nanometers or 1 micron, right? And that you can grow it and you can learn about surface conditions enough so that you can grow a single crystal, in a two-dimensional way rather than, under 3D conditions. Then I think that the responsibility all of a sudden goes from the material scientist to the physicist to the chemist, right? It goes to the surface. So you really have to put a lot of effort on surface chemistry, right? How do you so you have to go to selective processes. One of the things that's happening in the industry, in the electronics industry as a whole, is there's a lot of focus on selective epitaxy, selective growth of anything, right? You look at silicon germanium that is used in the source and drain of a silicon transistor that is in your pocket, right? Is a selective epitaxy process. And so as we go to the next phase or beyond, let's say, 3 or 4 nanometer gate length or technology, it's not a gate length, technology in silicon, in the next 5 or 6 years. If we wanted to adopt TMDs, for example, TMD would be a wonderful solution to the semiconductor industry problem of scaling the channel of the silicon. Why? Because it's a single layer, and it's great. You get reasonably high mobility, and you don't have to worry about surface scattering. You have to worry about all that stuff because the band structure takes care of that. The two-dimensionality takes care of that, right? And so, so the selective part would be really, really nice to develop. So I would say that if I had to put my money into processes, I would say selective processes and surface conditioning, surface chemistry, surface physics and understand it as, I mean, you put a lot of money into that, and then you have to create the tools that will enable you to do that. That's where I think it needs to go, because it's a little bit like graphene. I cannot imagine somebody coming up with a process where they have a single seed and growing at 300 millimeter or 400 or whatever, even 200, right? Unless you can convince yourself that grain boundaries are not important, and it's not true. Not in TMDs, and it's true maybe for graphene, not as much, right? But the TMDs, I think they're important.
Okay, I'm taking a question from the virtual question, say from Matej Sebek, who is online. So he said, thanks for the fascinating talk, Luigi. You've been mentioning huge differences between sulfide and selenide. What would be the major differences in terms of defects?
Practically speaking, people have found that it's extremely difficult to grow selenium-terminated surfaces that don't absorb oxygen or water or what have you. And so selenium is, selenides are very difficult. So some of the experiments that we did at UT Dallas, they had to basically coat the tungsten selenide with selenium, with extra selenium, so that you can then remove it. And so the defect chemistry is quite different. The vapor pressure is the bonding energy is different for the selenides versus the sulfides. Sulfides are actually more stable than the selenides. So in terms of chemical stability, the sulfides are much more stable.
Jose has another question. Christian.
Yeah, thanks a lot for the nice talk, Luigi. So you posted at the very beginning, like the big challenge that we have so many of these TMDs that we don't know what to select. So if you would have a bet, or if you look over it, or which criteria would be important, choose one of them. You just mentioned stability.
So I think stability is probably one of them. Obviously, there are some band structure consideration that need to, you cannot ignore, right? And so the question is, can you find? If I had to choose, I would prefer to work with sulfides rather than selenides, just from a stability perspective. The selenides tend to be more reactive than the sulfides, and the tellurides are tough also.
So Jose, you have another technical question? No, it's a philosophical question. It's technical philosophical. Okay. No. Okay. I have a question.
Philosophical technical question.
No, it's philosophical. Sorry. So you mentioned how important it is to devote efforts and in order to solve the problems that at the moment we have too many materials, too many challenges. But I mean, from firsthand how much it costs to develop a technology, right, and to develop a process and to industrialize. So, from your perspective, what is, from what you know from industry now, what is the industry position at the moment, semiconductor industry? What are the efforts which are also taken outside the industry? For instance, the graphene flagship has these experimental pilot line efforts where there are small industry and hopefully large industry can join in the future. So how do you see the balance of public support and interest from industry that can eventually need to pool all the efforts, right, in order to make this happen?
So, something happened probably about maybe 10 years ago when the industry kind of went away from having a focused effort on the ITRS, International Roadmap on Semiconductors. And now it's kind of every man for himself, right? There's always been this idea of keeping secrets. I mean, it's obvious, right? In the US, there's the Semiconductor Research Corporation where we invest in pre-competitive technologies and so forth. Today, when you look at let's say, the introduction of two-dimensional materials in, let's say, silicon flow, I think that people are keeping this information very tight. Because if it's a little bit like high-K metal gates, I always go back to this because this was a big, big deal for the semiconductor industry. And while we cooperated at the kind of pre-competitive level, I think that the amount of information that went out from industry, I mean, I was responsible for the high-K metal gate development at TI, and we knew so much more than what was known by universities. That we worked with them to solve specific problems, but at the end, we were running not one sampler at a time. We would do 24 wafer lots with 12 different splits, meaning 12 experiments each. And one of these would take maybe a week to do. And so you have 24 experiments in one, right? Somebody told me that a particular big company spent thousands of wafers to select a material. So imagine if you had enough resources to say, I have 10 TMDs and I need to select one. And you have enough resources to grow these TMDs, and then you select it. And that's what the industry sometimes does. And of course, we also need the theorists to guide us in the right direction. Without them, sometimes you're kind of blind, right? And so that's another important part. So industry, so the companies today, I think, are investing, but we don't know about it because it's not important to us. It's important to them, but not to us.
Okay, so that was another question, but it's quite related to the other one about defects. In Sumit Kumar asked, which has more defect, TMDs or TMO? TMO, it's transition metal oxide?
Yeah.
Should be oxide should be quite.
Depends. I mean,
I'll
I'll probably say that the chalcogenides have more defects than the oxides. But the defect chemistry of oxides is really very rich. And it's interesting and rich at the same time. It's different type of defects. But I think that it's kind of difficult to say which one has more. It's which one meets the requirements.
Okay, maybe I take, I don't know if there is any more question. I take a question, but you have a pin, blue pin, which is, I think it's a graphene flagship.
Yeah.
Your role as a scientific advisor for the past 10 years, together with Nobel laureate Geim Novoselov, von Klitzin-Fert. So you've been very privileged also to be part of this.
The kind of the plebeians of
No, privilege because you've seen many things and also, but what is your, I mean, after 10 years, next year we'll celebrate the 10 years of the graphene flagship. And probably now for graphene, we are close to some kind of, let's say, application, or I don't know if there are killer application. If you can tell us if what we have 10 years after was what you would have expected 10 years before, given your experience at TI, okay? And also concerning TMDs, they are so much more complicated than graphene, so much more complicated. So should we have to wait 1 century, 100 years before we can reach the same kind of development and close to application that we are now with graphene?
Okay, so I think that if I consider, what Jose is doing with graphene and with TMDs also, and I consider what the IMEC is doing with graphene and TMDs, while it would have been nice to have it earlier, actually I'm happy where they are, because it means that the direction of the flagship is in the right direction. You have to have enough resources in research, but you also have to have enough resources in development so that you can transfer this technology to production or pilot production or to industry. And so just from a personal satisfaction of having been part of this big maybe experiment, I think that a lot of good has been done, right? And the other thing is, it's brought a lot of people together. It's brought theorists, it's brought experimentalists, it's brought business people together in something that They just started from scratch, right? And so I think that's wonderful, because 10, 15 years ago, the semiconductor industry was by itself, and physicists and fundamental stuff, it was not important. Why? Because they were just doing scaling, just making it smaller and smaller and smaller, and the electrical engineers were taking care of all the simulations and modeling and all that, but physics was not part of it. So I think the great thing about the flagship, in a way, was really to bring everybody together and to solve a problem. Now, you had the second question, how long is it going to take us? I'm hoping that somebody, whether it's somebody in industry or in a research lab like IMEC, or maybe TSMC or Intel, they will come out and saying, these will have fantastic results with this, right? In that case, then resources would be just, the door will open, and then you'll have the resources will just flow into it, and you don't know what to do with the money. Actually, you will know what to do with the money, because there's a lot of issues. But they will address the problems. Because, I go back to the engineering and fundamental problems that we had with high-k metal gate, okay? It went from replacing one material. The idea was to replace one material, okay? We replaced not only one material, we replaced two materials, okay? And the work function. So let me go back a little bit. The company I was telling you about was trying to select a metal gate, okay? And they used thousands of wafers to do that, okay? Well, it turns out that none of the metals didn't matter, okay? They all had different work functions, but when you process it, you all go back to the same place, okay? But what was important is actually interfaces. And so they learned how to control an interface and control the work function, which controls the threshold voltage of the device. And so I think that that was a huge, and then they had to do CMP. And so the problem of TMD is complex, but if we can address the surface conditioning and the CVD, selective stuff, I think it might even be easier for a single element or a single TMD. It might even be easier than the integration of the high-k metal gate. The idea of having these layered transistors, right? Rather than having it thin this way, you take them on this side. Well, all of a sudden you've changed the game, okay? Because you cannot use silicon anymore. You have to use something else. And underneath, you don't have a single crystal anymore, right? So maybe the industry is forcing to go to two-dimensional materials just by definition of how the device is designed.
Okay, I think that was a good ending. Luigi, thank you so much again for your talk and the visit, and I guess we will continue discussing. So thanks you so much.